I have taught this course 4 of the past 5 years. On the left, we see the exam 1 average. On the right, we see the exam 2 average. This happens every year. I can do integrals. What integral do I do when? You did a lot better than this group. This is not unusual. And in most of the cases, it was the setup that was the issue. If there was an arithmetic mistake, I didn't care. You looked at a problem and went, I want to do this, and that is the complete wrong problem. Or your setup for your integral doesn't match the answer you got. I don't know what happened in the middle. Magic in some cases. I need you to do me a favor and go back and look at this critically with the key in hand. And then come talk to me. Because the third exam, usually the averages go back up a little. But the third exam is on the sequences and the things we're going to start covering today and for the rest of this chapter, and it's different. Sequences are already different enough that the third exam is substantially different. And then we'll see all of these integral questions again on the final. So I would recommend a substantial and careful examination of what happened in this exam, and then come talk to me. Meanwhile, back to sequences. We looked at a number of different sequences to ask if they converged or diverged. I want to look at this one now. We did just -1 to the n. Does this converge? Does this diverge? And how do you know? Yeah.
You know, like this idea, creating one and quadrant and quadrant is less than 1.
That was for integrals, and for improper integrals, the ones that went off to infinity. This number is doing something different. Write out the first 5 or 6 of these. Plug in n equals 1, 2, 3, 4, 5. Let's take a look at what's going on. Last week, when we looked at what was happening with -1 to the n, we saw that it bounced back and forth from positive to negative, or negative to positive. It just kept alternating sign. My denominator here continues to increase. What is the trend that I see happening? Well, but technically I can't say that, because 1/2 is bigger than -1, and 1/4 is bigger than -1/3. So smaller isn't quite it. They're getting closer to 0. They're getting closer and closer to 0, which means I'm not looking at the numbers themselves. I'm looking at their absolute value. If I take the absolute value there, what happens to the number on top? Leo. Always. And it's always a 1 then. The bottom is n is going to n is always oh. So I can think of looking at this as trying to figure out if there's something I can do from here. And I do know that does go to 0. Because the bottom keeps getting bigger and bigger and bigger and bigger and bigger, and the top stays 1. That's asymptotic to 0. It turns out that when I look at absolute value, that's a stronger condition. If I know the absolute value goes to 0, then terms without the absolute value also go to 0. And that means that for our example, since this piece is going to 0, that means this piece must go to 0. This sequence of numbers, 1 over n, is called the harmonic sequence. Anybody got any idea why?
It changes from negative to positive.
No, this one. The one where they're all positive is called harmonic. This one, with the switching, is called alternating harmonic, because it alternates from plus to minus. But the 1 over n part is called harmonic. This has to do with the lengths of strings and the notes they play and frequencies. If you take a string and you cut it in half, you get an octave. If you cut it in third, the 2/3 to 1/3 makes a perfect fifth. If you cut it in quarter, you get 2 octaves. These numbers give me musical ratios. This is why in Greek antiquity, music was considered a mathematical science. You're all musicians. Now, the alternating harmonic part and this harmonic idea, again, will come back to us later, either later today or tomorrow. Might actually be next week, I'm not sure. We'll see it again. What happens here? Yeah.
That'd be like, we're gonna 1/2 the end, it's radius of 1/2.
Well, but I can leave it just with the 2 on the end, right? This should be 1/2, then 1/4, 1/8, 1/16, 1/32, 1/64, and so on, right? What is going to happen as we go off to infinity?
So we get smaller and smaller exponentially.
Which means this goes to 0. Now, I like that idea, Leo. I like thinking of 1 over 2 to the n as if it was 1 to the n over 2 to the n, because 1 raised to any power is just 1, which makes this 1/2 to the n. Wait a second. Let's make this one negative. Again, let's write out what's going on here. I get negative 1/6, then I get 1 over 36, then I get negative 1 over 216, and then 1 over 1,296, and negative 1 over really big 7,776, and so. All right, wait a minute. The top is flip-flopping back and forth. But if I looked at absolute values, wouldn't the absolute values keep getting smaller? So I'm back in this sentence right here. I can say, oh, this is also going to go to 0. sequences like this can be generalized to look like some number to a power. And this sequence would look like r squared, r cubed, r to the fourth, and so on. Again, if we think of these as building blocks, we can actually think of this geometrically. And that is, a square, a physical square, a cube. Again, historically, when a Greek mathematician ran into this power, do you know what he called it? A square square. And a square cube. And so they thought geometrically. And to that, this is called a geometric sequence. Well, it turns out that I can compute these limits without fail. All I need to know is r. Based off of these two examples up here. I take a fraction, I take a power, the fraction gets smaller. What numbers, when you take powers, get bigger? Whole numbers, all the time? Oh, wait a second. There's a whole number that when you take any power of it doesn't change at all. 1. 1 to the 1 to the 1 is still 1, right? -1 goes -1, +1, -1, +1. So there's a dividing line. Now, I am a visual person. So I'm going to draw you a number line. I want you to put a dot somewhere on this number line for your value of r. And I don't care if r is large or small. I'm going to use 1 and -1 as my dividing line. I don't care if you put it outside or inside. Put a dot somewhere on this number line. Dominic, where'd you put your dot? By 2. So, when I start squaring that or raising it to other powers, right? 2 times 2 is 4, then 8, then 16, and I just go woof off that way, right? Kind of where'd you put yours? Past 1. It's going to go that way, right? Where'd you put yours, Maddie? Woof. Anybody put it anywhere else other than on the right side of 1? Where'd you put yours, Nora? And if I do 1/2, then I get a quarter and an eighth and a 16th, and we go this way. What if I start with a negative number? If I started with -2, I'd go to 4, and then I'd go to -8, and then I'd go to -16, and I'd keep getting further and further away, don't I? And if I start with a negative number that's in here, well, then it becomes positive, but it's smaller. And then it becomes negative, but it's smaller. And then positive, but it's smaller. And I crash my way in, don't I? The only two numbers that are weird, the boundary edges, are 1, because 1 stays where it is. It doesn't do anything at all. It just goes 1, 1, 1, 1. And -1 keeps going back and forth to itself. So what we've got here is a dividing line. This is a very important result we will use a whole bunch later. A geometric sequence either converges only if the number, the ratio, that's why we call it R, is between -1 and 1, or it blows up. An interesting note, this works for more numbers than just real numbers. This works for complex numbers too. There's some really neat stuff with sequences and complex numbers. I'll save it for later. Questions? So put a star by this result. We're going to need it later. Now, Maddie, I corrected you quite firmly when you said they're getting smaller. I want a new definition. A sequence is monotone increasing. The word monotone is optional here. If the numbers keep getting bigger or stay the same. A sequence is monotone decreasing if the inequality goes the other way. And that's why I didn't want to use getting smaller or getting bigger, because increasing, I should always see those numbers going up. But if I keep going back and forth between negative and positive, then sometimes I go down and sometimes I go up. By the way, if I just use the word monotone, it could be either increasing or decreasing, but it's got to be one or the other. And so our alternating sequence was not monotone. And some sequences follow patterns that don't have that strict always up or always down. Oh, I didn't use the word strict, did I? And you'll notice those inequalities are not strict. If I said monotone strictly increasing, I change that to be strict inequality. If I said strictly decreasing, I change that to be strict. So, how do I know if the terms of a sequence are monotone? Yes, Leo.
Clearly increasing each time or clearly decreasing every time.
Right, but I need to show that. Yes?
Yes, sir.
So I would hope that if I were to say, hey, this sequence is monotone decreasing, that you would agree with me. How could you show that this sequence is decreasing? Yes, there.
Like I was thinking, like I could do it maybe like 5 terms for, say, like it could be 5/1 and 5/2 and 5/3, 5/4 and 1 for less than.
And I would agree with you that for the first few, that's true. I want to know it's true all the time. And a list of examples, even a big list of examples, is not proving that this is always going to go down. But I like your idea. So what if instead of doing it for one specific number, I did it in general? What happens when you make the bottom of a fraction bigger? The fraction gets smaller. Check. That was easy. But if my sequence is more complicated, this could be hard. See, now I start comparing things. I do 1/2. The next one is 2/5. The next one is 3/10. I think those are getting smaller. But the problem is that the top of the fraction keeps changing as well as the bottom of the fraction. So if I were to try and look at n/n² plus 1 and compare it to n+1/n+1² plus 1, oh. I'm pretty sure I could do a bunch of algebra that would show that this is going to work out, but that algebra looks like it sucks. And this isn't really an algebra class, is it? Technically, this is the calculus class. So let's do some calculus instead, damn it. What could I do to show something is decreasing in calculus terms? Last semester. How do you know when something's decreasing? Its derivative is negative. Derivative of what? I don't remember what. On Friday, I said that if we had a sequence, we could replace it with a function. If I can find an f of x, so that its terms match my sequence, then I can look at f of x instead of my sequence an. Well, all I have to do is take all of those n's and replace them by x's, and now I have a function. And if for all n bigger than 1, derivative is negative, then it's decreasing whenever n is bigger than 1, which is where my sequence lives. So I have just turned a sequence problem into a derivative problem. Yay, I like derivatives. Derivatives were easier than integrals. Let's do derivatives. What's f prime of x? Yes, Leo. Walk me through the actual calculation. Bottom minus
x times 2x
over
squared plus 1 whole squared.
root of the top times the bottom, root of the bottom times the top over the bottom squared. Let's do the algebra to simplify this. I have x squared plus 1 minus 2x squared on top, x squared plus 1 squared on the bottom. So I get 1 minus x squared on top, x squared plus 1 squared on the bottom. Maddie, you're looking at me like this is bothering you. Talk to me.
It would be x to the 4th.
I'm going to leave the bottom as is. I promise there's a reason for leaving the bottom as is. Please notice the bottom is always something squared, and the bottom is never 0, so the bottom is always positive. The only place I have to worry about its change in sign is the top. And that's only 0 plus or minus 1. Which means I have my critical numbers, I can make a sign chart, and I can figure out where this thing is positive and negative. Nope, this one's run dry. When I put in a test number smaller, well, really, I only care about where it's over here, right? I really only want to know what's going on for the bigger than 1, so I want to know what's going on over here. I put in 2, I get 1 minus 4, that's negative on top, positive on bottom, negative, we're decreasing. Yay. I don't need any of the stuff on the left, because I only care what's happening from 1 on. Calculus to the rescue. Leo, interestingly enough, there are a large number of sequences that start positive and start increasing and then decrease much further on. We can actually construct a sequence that increases for as many terms as you want and then starts decreasing. Or decreases for as many terms as you want and then starts increasing. It's actually very easy to build a sequence that looks monotone for the first 100 or 200 or 1,000 terms, but actually isn't. That's why I have to do a proof like this rather than just look at a list of numbers. But that's not an uncommon idea to start with. Hey, look at the first 100. Are they doing that? And with computers, I can look at a lot of numbers very quickly. But this didn't require me to have any list. Questions? A sequence is bounded above if it never goes past some number capital N. What do you think bounded below means? Leo? Exactly. And I'm going to change the symbol to be a little m. One more definition. A bounded sequence is bounded above and below. So if you've got both an upper threshold and a lower threshold, then you are bounded. Why? Why do I care? Because now I can determine whether or not a limit exists for my sequence without finding the limit. Now, I don't even want to try and justify this statement with anything other than a picture. Picture for this is actually really good. Draw a graph, and then we have some lower limit, little m. Do you want little m to be positive or negative? Somebody make a call. Positive or negative? Then little m is some horizontal line right here. That's y equals little m. And then way up here, I have y equals capital M. Your sequence must be between those two lines, yes? That's what it means to be bounded. It's monotone. That means it's either always going up or always going down. If your sequence is monotone increasing, then your dots have to do that, don't they? And if your sequence is monotone decreasing, they have to do that. You've got to have a limit somewhere, or you have to come away from that and go back. Those are asymptotes. If you are monotone and bounded, you must have a limit. Questions? Sequences of numbers, in and of themselves, sound like an interesting diversion. It doesn't sound like it has very much to do with any calculus. Even though I just used some calculus in here, it doesn't sound like this really. Why was this studied in calculus? Well, it turns out that what was actually studied that I think was far more important than sequences was something called series. A series is a sum. Now here's the twist. I want not just a sum of numbers, I want the sum of infinitely many numbers. Okay, what the absolute is going on here? Wait a minute. Calculus is the study of infinite things. When we started with derivatives, we looked at infinitely small differences to make secant lines and tangent lines. That's how we got limits. We said, hey, we're going to look at epsilon, and epsilon is some itty bitty teeny weeny number. And then we started doing integrals, and we looked at areas of rectangles, and then we made those rectangles thinner and thinner and thinner and thinner and thinner and thinner, and we added up. We did a Riemann sum. A Riemann sum is a type of a series. So in order really to understand how integrals work, I have to understand how series work. This approach is what allows us to do things like we did in chapter 7, where we approximated an integral, right? We approximated an integral with a sum. So how do those sums work? So the question is, if I add up an infinite number of things, does it make any damn sense? Huh. I suppose it depends on how we look at our addition. I'm going to start with what I think is an easy sum. Capital sigma means add them all up. That's what we were using back in Riemann sums, what we're doing back in Calc 1. This says start at 1, go to infinity, and add 1 over and over and over and over every time. If I asked you what this added up to, what's your answer? Say it louder, Maddie. Infinity. How can I show that? It makes sense that you would think this blows up. You're never going to stop. You're just going to add one more and add one more, and you're just going to keep marching off to infinity. Let's consider, instead of trying to add all infinitely many numbers up at a time, we add up the first few. Leo, I'll give you an idea. I'm going to add up the first few. And I'm going to call this a partial sum. Now, if I want to be technical about it, the partial sum, Sn, would be from 1 to n of our terms. So let's write out what happens. S1, S2, S3, S4. Let's see what we get here. But by its very definition, S1 is 1. I go from 1 to 1, so I only write down 1, 1. When I do S2, I write down the first 2 of them. When I write down S3, I write down the first 3 of them. S4 writes down the first 4 of them. What's Sn? Leo? It'd be n times, right? So it'll be n. Now here's an interesting result. If I think of Sn as a sequence, I can now ask, hey, does that sequence have a limit? And if we have a limit, then I'll know something about my series. But in this case, what is the limit as n goes off to infinity of n? Yeah, and that's divergent. On the other hand, let's consider a geometric. And not just any geometric, a geometric whose sum we looked at, whose sequence we looked at earlier. If I wrote this out, this would be 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32, and it keeps going. Same idea. Instead of trying to figure out what this total is all at once, I'm going to look at the partial sums. And this is where my intuitive reaction probably is going to fail me. Because I say to myself, hey, these numbers keep getting bigger. I keep adding on another little positive bit. I'm adding on and adding on and adding on. This should blow up. But I would like you to add all of those up and give me a fraction with a common denominator in each row. So the top row is already 1/2. But the second row is 1/2 plus 1/4. That's 3/4. Common denominator 4. If I use a common denominator of 8 down here, what do I get? 7/8. And then here, 15/16. Ooh. Let me extrapolate a pattern. my common denominator in the bottom will be 2 to the n. And the top will be one number less. Now we can check that. If I add up the first 5, S5, 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1 over 32. Well, I know these make 15 over 16 plus 1 over 32. Double that to get the common denominator. That's 30 over 32. Lo and behold, that's 31 over 32. My pattern seems to work. This is called an inductive argument. And if I really wanted to be anal retentive about it, I would say we have to prove this inductively. No, I'm not doing that. This is good enough. Hey, wait a minute. If that's our expression for our partial sum, I can now ask, does that have a limit? Now, your first reaction might be, how the f am I supposed to know? You could, if you really wanted to, do L'Hopital's rule. Because that's infinity over infinity, isn't it? I don't want to do L'Hopital's rule. Instead of doing L'Hopital's rule, I'm going to do Snell's rule. And I'm going to split this fraction into 2 separate fractions. What's that first fraction simplify? Leo? It would be better. It'd be 1 to the n is always 1. Aha. I'm just going to leave that as 1 over 2 to the n for the moment. Because then I can say, hey, wait a minute, the bottom is getting bigger, but the top is always 1. What happens as n goes off to infinity to this fraction? It's 0. I have a limit this time. I claim that if you add up 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/30, and you keep going with all of those powers of 2 in the bottom, to infinity, you get 1. I like this idea so much, I'm going to define the value of a series this way. For any series, we look at the partial sums, and we look at the limit of the sequence of partial sums. If those converge, say to some number s, then we say that our sum converges to S and that the value of the sum is equal to S. Otherwise, we say that our series diverges. And I will go more into what these mean with some more examples and even a very nice picture for the one we just did. I'll show you the picture really quickly. You'll like this. Take a square, a 1 by 1 square. What's the area of that square? So cut it in half. That's 1/2. Cut the remaining piece in half again. That's 1/4. Cut the remaining piece in half again. That's 1/8. The remaining piece in half again. That's 1/16. That's 1/32. I keep cutting in half. Am I ever going to get bigger than the square? But my sequence of partial sums is monotone and it's bounded above. My sequence is increasing. I keep adding another little bit of area. It's got to be going up, but it's got an upper limit. It must have a limit. That's why we needed sequences to do series. All right. I will talk to you all more about this tomorrow. I will see you all then. Thank you. Have a wonderful rest of your day.